This video is going to be on section 6.3, the kernel and range of a linear transformation. Okay. Let's start the discussion with having a linear transformation. So definition, let's let T, which goes from V to W, be a linear transformation. We have two sets that we can naturally define from this. So first, the set of all vectors v in V such that T of V is equal to the 0 vector. Remember, that's in W, is called the kernel of T. And we denote it like this. We write KER. This means kernel of T. In other words, the kernel of T is equal to the set of all V in V such that T of V is equal to the 0 vector in W. You can notice right away from the definition that this is a subset of V, right? This is a subset of V. Next, the subset of W consisting of all transformed vectors from V is called the range of T, the range of T, and it is denoted like this. Now, your book actually puts parentheses around the T. I don't necessarily need that to happen here. It's obvious if you're just doing one thing that you're talking about what's right in front of it. So I usually think the parentheses are overkill. Just understand I might leave them off sometimes because it's not really necessary if you're just doing one thing. Okay, we could clearly see here, by the way, that these are both subsets. So let me go to the next page to give you a visual. So note the kernel of T is a subset of V, and the range of T is a subset of W. Now, I want to draw a visual to help you understand what these look like. So let's draw these two big vector spaces. Let's say that this guy is V, and let's say that this guy over here is W. So let's start by drawing a representation of so we're going to call this guy right here the 0 vector, and let's say that this is the 0 vector in W. There are a whole bunch of guys over here that all get mapped to that 0 vector using t. Okay? So this subset that gets created over here, this is the kernel of t. Okay? You can see that kernel of t lives in V. It's a subset of V. Now, what about the range? I'm going to use a different color for this. Okay, let me go with, I'll use green. How about that? So if you look at all of V, it's wherever V lives over here. So maybe it looks something like this. And all of V looks something like this. So this guy over here is the range of T. Okay? So this is a visual representation of what the kernel of T and what the range of T looks like. Okay? All right, so let's go to the next page here. We clearly know that these are subsets, right? This is the definition. So these are both subsets but are they subspaces? The answer is yes. So let's write this as a theorem so we have a nice statement here to look at. Let's let T, which maps from V to W, be a linear transformation. Then the kernel of T is a subspace of V, and the range of T is a subspace of W. Remember, this is a stronger statement than just saying they're subsets. Being a subspace means that they actually inherit the structure of the space that they live in. So I'm going to call this statement 1, and I'm going to call this statement 2. And so we are going to prove these things. So let's do the proof of statement 1 first. Okay. Let's take two guys that are in there. Okay. And let's also take a C that's a real number. Remember, to show that something is a subspace, we need to show that when you add them together, two things in there, that it's closed under addition, right? So how do we show that something is in the kernel? You have to take T of that thing. It's all the guys that go to 0, right? So what is T of V1 plus V2? Well, by property of linearity, this is just V1 plus T of V2, but these are both 0 because V1 and V2 are in the kernel. So this means we have 0 plus 0, which is equal to 0. So this implies that the kernel of T is closed under addition. Okay, let's now show that it's closed under scalar multiplication. So what is T of C times V1? We know that we're allowed to pull C out because of linearity of a linear transformation. But this is just C times the 0 vector, which is equal to the 0 vector. What we just showed is that T of CV1 is equal to the 0 vector. In other words, kernel of T is closed under scalar multiplication. So we have proved part 1. This means that kernel of T is a subspace. Okay, let's go ahead and prove part 2 now. So proof of part 2, we're going to let W1 and W2 both live in the range of T, and again, take a real number. We need to show that if you add these two things together, you're still in the range. So let's use the definition of being in the range. This means that there exists a V1 and a V2 in V such that T of V1 is equal to W1 and T of V2 is equal to W2. So what is T of V1 plus V2? Well, this is equal by linearity to T of V1 plus T of V2, which is equal to W1 plus W2. So what we just showed is that V1 plus V2 maps to W1 plus W2, which means that W1 plus W2 lives in the range of T, which means that the range of T is closed under addition. Okay. So now let's show that it's closed under scalar multiplication. What would T of C V1 be? This is equal to C times T of V1, which is C times W1, which is in the range. So this means that range of T is closed under scalar multiplication. What does this mean? This means that the range of T is actually a subspace of W. Okay, so what we now know is that these two things are subspaces, but question, have we seen them before? So let's talk about a special case here. So a special case, the special case here is going to be what happens if we have T being a transformation from Rn to Rm. So let's suppose that this is a linear transformation. Remember what we learned? We learned this implies that there exists an A, some m by n matrix such that T of x is equal to AX. So let's actually sit here and think about what the kernel of this transformation would be. The kernel of the transformation is defined to be, remember, it's all of the x. In this case, it would be all of the x in Rn such that T of x is equal to the 0 vector. But this is the same as the set of all x in Rn such that, remember, t of x is just a times x, so that's the same as saying this. But this should look familiar to you. When you look at this relationship, this set is specifically the null space of A. So what we just learned is that the kernel of T is the same as the null space of A. What about the range? This one is a little bit harder to spot. Okay, but let's think about what the range is. The range is the set of all T of x such that x is in Rn. But T of x is the same as the set of all Ax such that x is in Rn. Now, for us to notice this next part, we have to remind ourselves of how matrix multiplication works. Okay, let's suppose that A would equal A1, A2. Remember, A is an m by n matrix, so how many columns does it have? It has n columns. So let's suppose that these are the n columns. And let's say that x is equal to x1 to xn. If we make those two definitions, then this actually becomes as follows. This is x1 a1 plus x2 a2. These are vectors, plus xn an. This is just the definition, or one of the definitions of matrix multiplications, such that xi is in R. Okay, so what did we just do? This set is literally the span of the columns of A. In other words, this is the column space of A. So let's write down the conclusion. So the conclusion of what we just wrote is if T is a transformation going from Rn to Rm with matrix A, then the kernel of T is the same as the null space of A, and the range of T is the same as the column space of A. Two very cool facts that are true about any linear transformation that goes from Rn to Rm. So let's go ahead and do an example. Okay, our first example here, this new idea. Let's let T, which goes from R3 to R2, be the linear transformation with matrix A, and this is going to be the following matrix: 1, -2, -2, 4, 5, -10. So the question is to find the kernel of T and the range of T, as well as their dimensions. So let's start with the kernel. The kernel of T is going to be the same as the null space of A. So all we really have to do is find the null space of A. So let's go ahead and remember, let me remind you guys of what the null space of A is. It's the set of all x in this case, it's going to be in R3, right? Set of all x in R3 such that AX is equal to the 0 vector. So let's look at that system, right? We need to translate this system right here into matrix form. So let's go and write down the augmented matrix. This is going to be 1, -2, -2, 4, 5, -10. Okay. We can see, oh, I also need to put this here. So we could see that if we add -2 row 1s to row 2, we end up with 1, 0, -2, 0, 5, 0, and 0, 0. Okay? So let's go ahead and we need 2 free variables, right? Because this guy has no leading ones and this guy has no leading ones. So I'm going to create 2 free variables here. So let's say that x3 is t and x2 is s. Then this means that x1 is equal to 2s minus 5t. Okay, so this means that our solution set is equal to the following. We have all vectors of the form 2s minus 5t, s, and t, which, if we break this up, doesn't this equal s times 2, 1, 0, plus t times -5, 0, 1? So we just found that all solutions have this form. In other words, this implies that the kernel of t is equal to the span of those 2 vectors. And by the way, because those are 2 vectors that span the entire thing, and we actually reduced it to row echelon form, these 2 guys are linearly independent. In other words, these 2 guys span the whole thing. They form a basis, okay? So this means also that the dimension of the kernel is equal to 2. Okay, so that's the answer to the first part. We're looking for the kernel and its dimension. Let's do the range now. Remember, the range of t is going to equal to the column space of A. To find the column space, you need to put it in row echelon. And if you come back here, remember that you look for the column that has a leading 1. So this guy has a leading 1, in which case it corresponds to the first column over here. And so what that means, that the range of t, which is the column space, is actually equal to the span of just that column, which is 1, -2, right? So the dimension of the range of t is 1, right? There's only 1 vector inside of there. Okay, so this was our first example using kernel and range. Let's look at a second example. let's let S be a linear transformation from 2 by 2 matrices to 2 by 2 matrices given by S of A is equal to A minus A transpose. Okay, kind of an abstract little matrix or transformation here, but we are taking a matrix and subtracting its transpose from it. So let's go ahead and find, we're going to do the same exact thing. We're going to find the kernel of S and the range of S as well as their dimensions. Let's start with the kernel of S. The kernel of S is the set of all matrices such that S of A is equal to the 0 matrix. But what is S of A? Don't forget that S of A is really A minus A transpose. So this is equal to the set of all A such that A minus A transpose is the 0 matrix. But if A minus A transpose is the 0 matrix, isn't that the same as the set of all A such that A is equal to its transpose? But if a matrix is equal to its transpose, this is the same as the set of 2 by 2 symmetric matrices. Interestingly enough, we just found the kernel. It's the set of 2 by 2 symmetric matrices, which is a set that we understand. So what are the set of 2 by 2 symmetric matrices? If we wanted to write a basis for it, so a basis for kernel of S is what? Well, 2 by 2 symmetric matrices all take on this form, A, B, B, C. So a basis would be, we have 1, 0, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 1. In other words, the dimension of the kernel is equal to 3. Okay, so we found the kernel and we found its dimension. Let's do the range now. The range is equal to the set of all S of A such that A is a 2 by 2 matrix. But this is the same as the set of all A minus A transpose such that A is a 2 by 2 matrix. What is A minus A transpose? Well, take any matrix and subtract its transpose from it, and let's see what you get. If you take A, B, C, D, and you subtract a C, B, D, because that would be its transpose, and this is all possibilities, right, of matrices that look like this. What do we end up with? We actually end up with, think about it, if you take these two matrices away, you actually get a 0 here and a 0 here, and then a B minus C, and then a C minus B. Okay, but what is that? These are actually the set of all matrices that look like this. So what would that be? This is actually the set of 2 by 2 skew-symmetric matrices. Interestingly enough, both symmetric and skew-symmetric matrices popped up in this problem. What would its dimension be? Well, a basis for the range is equal to what? Well, you only need one free variable here, right? 0, 1, 1, 0, right? This would be a basis. In other words, the dimension of the range of S is equal to 1. Now, the next theorem I'm going to state is extremely important, okay? This theorem has a name. Anytime you name a theorem and you don't just call it theorem, you know it's important. This is called the general rank nullity theorem. Or if we want to abbreviate it, it's RNT. So let's let T from V to W be a linear transformation then, I guess there is an important thing I should say. It's not just a linear transformation. Let's suppose that V is a finite dimensional vector space. This is important. We have to assume that V does have a finite dimension. Then, and this is the cool part, the dimension of the kernel of T plus the dimension of the range of T is equal to the dimension of V. This is an extremely useful formula that we are going to use all the time. This is saying that if you were to add the dimensions of the kernel and the range, you actually end up with the dimension of V, which is interesting. Keep in mind that the kernel, remember, lives in V, and the range lives in W, and yet they both add up to the dimension of V. Okay? So let's go back really quick just to verify that this is actually true in our previous example. So if we come back here, let's see, we did 2 examples, right? So if we come back here, I want you guys to notice that the dimension of the kernel was 2, and the dimension of the range was 1. So 2 plus 1 is equal to, what's the dimension of V? Let's go back. The dimension of V is 3. And it is true, isn't it? 2 plus 1 is indeed 3. Let's look at this example. The dimension of the kernel is 3. And the dimension of the range is 1. What's the dimension of V? Remember, the vector space is that guy. We know that 2 by 2 matrices have a dimension of 4. Notice, in our last example, it is true that 3 plus 1 is equal to 4. Okay, so this shows at least that the rank nullity theorem does apply to our previous example. It applies to every single linear transformation of vector spaces. What's really neat about this is we can use this to actually figure out what subspaces are without actually calculating, because the dimensions really limit the arguments here. So we're going to do one more example. Let's let T, which goes from P2 of R to R2, be the linear transformation given by T of, I got to tell you what we do to the transformation. So T of P of X is equal to P of 2 and P prime of 4. Weird, right? But this is in R2, so this is well defined, and we know we are allowed to take the derivative of any polynomial, so what I just wrote down does make sense. So the directions are to find the kernel of T and the range of T as well as their dimensions. So let's go ahead and do the kernel of T first, okay? So let's write this down. The kernel of T is equal to, it's the set of all P of X in P2R such that T of P of X is equal to 0. We're talking about the zero polynomial here. Or sorry, not the zero polynomial, the zero vector. All right, I said that wrong. What is this equal to? Well, this is equal to the set of all P of X in P2 of R such that, remember, T is written up here such that P of 2 is equal to 0 and P prime of 4 is equal to 0. Both those things have to be true for this guy to be the zero vector. Let's go ahead and actually write down those as a polynomial here. This is the set of all a plus bx plus cx squared. Remember, that is a polynomial of degree 2, such that if you plug in 2, you get 0. A plus 2b plus 4c is equal to 0. And if you take the derivative and plug in 4, what would the derivative be? Well, the derivative of that guy is b plus 2cx. So if you plug in 4, you get b plus 8c is equal to 0. But wait a minute, aren't we just solving a system of equations? So what is the solution set here? Because we actually just need to solve this system here. So what do we get? We get, well, this is the system we want to solve. 1, 0, 2, 1, 4, 8, and 0, 0. Okay, we've actually almost got this solved already, but I'm going to go ahead just to put it in reduced row echelon so that it will give us an even nicer answer. we're going to add negative 2 row 2's to row 1, and we end up with 1, 0, 0, 1, negative 12, 8, and 0, 0. Remember, guys, we're solving that system, so these are the coefficients to A, B, and C, right? That's what we're looking at here. So let's go ahead and create our free variable. If we call C equal to T, then that means B is equal to negative 8T, and A is equal to 12T. So let's come back. This means if we come back to what this was, what we were going, so let me highlight here. This equal sign right here, let's keep going. This is equal to, we now know what A, B, and C are, so let's go ahead and write that in. It's all polynomials that look like this. 12t minus 8tx plus tx squared, such that t is a real number. But if we pull the t out, you can clearly see that this is just the span of the single polynomial 12 minus 8x plus x squared. So we found it, okay? The kernel of t, let's write this on the next page. So this implies that the kernel of t is equal to the span of 12 minus 8x plus x squared. So we know what the kernel is, and we could say what its dimension is. The dimension of the kernel is just 1, right? Because there's only one polynomial there that we're spanning. Now, you'll notice that I haven't used the rank nullity theorem yet, but I am about to use it. So, okay, we now want to find the range of t, right? But let's go ahead and write down the rank nullity theorem. By the rank nullity theorem, we know that the dimension of the kernel of t plus the dimension of the range of t has to equal the dimension of v. What's v in this case? Let's go back. V was P2R. But we know the dimensions of 2 out of the 3 of these things, right? The dimension of the kernel is 1, because we just did that problem. And we know the dimension of P2R is 3. So what does that mean? That means that this guy has to be 2. Now, just because we know a vector space's dimension, it doesn't mean we know what it is. However, in this case, we do. Because recall that the range of T is a subset, or a subspace, of what? Of W, which in this case is, coming back over here, R2. So if we come back here, this guy is a subspace of R2, and it's 2-dimensional. What does that mean? It means it has to be all of R2. So we just saved a lot of time there. In other words, we know that the range gives you everything. So coming back here, it means that this transformation gives you every single vector in R2. Okay, so there we go. There's the range, and there is the dimension. And that concludes this video. Thank you very much for watching.